The last time you flushed a toilet, you didn't just get rid of waste. You triggered one of the most sophisticated engineering systems humans have ever built, a system so good at its job that you never think about it. In the next 10 minutes, you're going to follow exactly where everything goes, and discover why a simple curved pipe invented in 1775 still protects your home every single day. When you press the handle, gravity does the first job. Water from the cistern drops fast enough to create a siphon effect that pulls waste down, not water pressure. Most people assume it's pressure. It isn't. It's physics. The force of that falling water creates a brief vacuum that draws everything in the bowl downward with it. It happens in under 3 seconds. It has worked this way for 250 years. Below the bowl is a curved pipe called the S-bend, invented in 1775 by a watchmaker named Alexander Cumming, not a plumber, a watchmaker. He curved the pipe to hold a pocket of standing water at all times, blocking sewer gas from rising back into your home. Cumming had no understanding of germ theory. Nobody did in 1775. He solved a problem he couldn't scientifically explain. His solution still exists, unchanged, in almost every toilet on Earth today. The next time you look under a sink or behind a toilet, you'll see that same curved pipe. Invented a decade before the French Revolution. Still working perfectly. From the S-bend, waste enters your building's drain stack, a vertical pipe running the full height of the building. In a skyscraper, that stack might run 50 or 60 floors. At the base, flow turns horizontal and exits through the main drain line buried below the foundation. This pipe runs under your street at a precisely calculated angle, a quarter inch of drop per foot of horizontal run. That slope is not arbitrary. Too steep and water outruns the solids, leaving them stuck in the pipe. Not steep enough and nothing moves at all. Getting that angle right is one of the most fundamental calculations in civil engineering, and it has to be correct for every single pipe in the network. Consider the scale of what exists beneath your feet. New York City's sewer system contains over 7,400 miles of pipe, enough to circle the Earth more than twice. It serves 8.3 million people every single day without most of them ever thinking about it. London's sewer system was built in the 1860s after the Great Stink of 1858 made the River Thames so toxic that Parliament itself had to evacuate. The stench was so unbearable that curtains soaked in chloride of lime were hung in the windows of the Houses of Parliament just so MPs could continue working. That crisis forced the construction of one of the greatest infrastructure projects in history. Parts of that original Victorian brickwork, built 160 years ago, are still carrying London's waste today. At key junctions throughout the network, massive pumping stations push the flow uphill where gravity alone isn't enough. Some of these stations are engineering marvels in their own right. The Crossness pumping station in London, built in 1865, is considered one of the finest examples of Victorian ironwork in the world. It was designed to be beautiful because its engineer, Joseph Bazalgette, believed that infrastructure built for the public deserved to look worthy of its purpose. Today it sits largely forgotten beside the Thames, still operational, still moving waste for a city that has no idea it exists. In many cities, combined sewer systems handle both wastewater and stormwater in the same pipes. This design works efficiently in normal conditions. But during heavy rain, the volume can exceed what the system can handle, forcing a choice between two bad options: let sewage back up into homes, or release untreated overflow directly into rivers. Engineers have spent decades designing relief tunnels and underground holding tanks specifically to manage those surges. London's Tideway Tunnel, a 25-kilometre super sewer being drilled beneath the Thames, will intercept 95% of those overflow events when complete. It costs over £4 billion. It will be invisible. Nobody will know it's there. Everything eventually arrives at a wastewater treatment plant. The process happens in 4 distinct stages. First, physical screening. Bar screens catch everything that shouldn't have been flushed: wipes, plastics, rags, and things that defy explanation, protecting the equipment downstream. Second, primary settling. Wastewater sits in large circular tanks for 1 to 2 hours. Solids sink to the bottom as sludge. Oils and grease float to the top and are skimmed off. What remains in the middle is still roughly 70% contaminated. Third, and this is the stage most people have absolutely no idea exists: biological treatment. Billions of bacteria are deliberately cultivated and introduced into the water. These microorganisms eat the organic contaminants. This isn't a chemical process. It's a living ecosystem, engineered, monitored, and maintained inside industrial tanks, consuming the waste so the water doesn't have to carry it. The bacteria's metabolic processes accomplish in hours what would take nature years. The operators of a wastewater treatment plant are, in a very real sense, farmers. They tend to billions of living organisms every single day to keep your water clean. Fourth, UV disinfection. Ultraviolet light passes through the treated water, destroying any remaining pathogens without introducing a single chemical. Samples are tested continuously against strict regulatory standards. The water that exits a modern treatment plant is cleaner than most natural rivers. In California, Singapore, and Namibia, it is processed further and returned directly to the drinking water supply. The water you flushed this morning may become the water someone else drinks next month. That is not a metaphor. That is the actual water cycle as engineered by humans. The sludge collected at the bottom of the settling tanks doesn't disappear either. It's processed separately through anaerobic digestion, a process where a different set of bacteria break it down further in sealed tanks with no oxygen. That breakdown produces biogas, primarily methane, as a byproduct. Many modern treatment plants capture that biogas and use it to generate electricity, powering their own operations. Some produce more energy than they consume. The waste powers the system that processes the waste. A closed loop, invisible, running continuously beneath the city. Now consider this number: 3.6 billion people, nearly half the global population, have no access to safely managed sanitation. No S-bend pipe. No drain stack. No treatment plant. No pumping station. Nothing. The infrastructure described in the last 8 minutes took over 150 years and trillions of dollars to build in the cities where it exists. Before it did, cholera killed tens of thousands of people in single outbreaks. Typhoid was endemic in every major city on Earth. The historian Stephen Johnson has argued that the sewer system saved more lives than any medical discovery in history, more than antibiotics, more than vaccines. More than any single thing medicine has ever done, the decision to move human waste away from human water supplies is responsible for the length of your life expectancy. You used it this morning without thinking about it. That invisibility is the point. The best infrastructure is the kind you never notice, until the moment it isn't there. Every flush is a brief interaction with one of the greatest engineering achievements in human history. A system built by people you've never heard of, solving problems most people never think about, maintained by workers who go unseen, running silently beneath your feet every single day. Every ordinary thing around you has a version of this story. A hidden system. An invisible layer. An engineering decision made generations ago that still shapes your life today. That's what this channel is here to find. Subscribe for weekly explainers on the hidden systems that run modern life. Next week, how the power grid stays balanced every single second of every day, and what happens in the critical 0.2 seconds before it doesn't.